Swayam Prabha. Digital India. Educated India.
Right. Okay, so that's what this formula means. Now, what does it give you? Well, you can work it out. You can work out the table, the truth table, all 8 possible combinations of PQR, and you write down the values of the results of G and of G, right, by substituting PQR and simplifying. And it turns out it has this nice little structure. You know, all the falses are here, all the truths are here, there are equal number of them. And if you look at it, it's basically false when there are 2 falses, and it's true when there are 2 truths in its input. So it's a majority operator. It takes 3 things, and you know, if all 3 are the same value, well and good, that's the output also. Otherwise, it goes with whatever is in majority. Okay. So there's another, you know, it's a not a binary operator, it's a larger operator, but this is something that has a name, the majority operator. But in general, not all formulas you know, correspond to named operators. And again, when you have you know, you can have multiple formulas that give you the same truth table. So here is another formula which also you can evaluate. It will come out to be the same truth table. Okay, so these 2 formulas are equivalent to each other. All right, so before I finish, just leave you with an exercise. There's basically a bunch of equivalences of formulas that you should verify. In all cases, in the brute force way to verify the equivalence is to build a truth table of the left-hand formula and the right-hand formula, right? So, you know, if you, here is the left-hand formula is, there's a proposition that has Q as a variable. And Q can have 2 values, as true or false. So for each value of Q, you write down what the formula, what the resulting proposition evaluates to. And do that for the right-hand side also, and you would see that they're the same values. Okay, that's how you prove equivalence. That's one way you could prove equivalence. Alternately, you could make logical arguments. So here is a contrapositive that we talked about earlier. If P then Q is the same as not Q implies not P, how would you reason about it? You could consider cases. You could consider, you know, if P is true, or actually in this case, it might be easier to first write down the expression in terms of this. So this is not P or Q, and this is not Q or not P. Not Q is just Q. So this is Q or not P. Q or not P is the same as not P or Q. It's a symmetric operator. So both sides are saying not P or Q. So that's why they are equivalent, right? So you didn't have to build the truth table to prove this equivalence. The distributive property is an equivalence of formulas involving 3 variables. And you know, yeah, it's instructive to think it through, write down the truth table if you want. And the important thing is and or are kind of on the same footing. And distributes over or distributes over and. And finally, the De Morgan's law, which shows how the not operator kind of distributes over and or, but it distributes in the sense that not of P and Q is not P or not Q. Again, you should think this through. You could think about it kind of using higher level natural language interpretations, or simply by writing the truth table and checking that the truth table for this formula and this formula are the same. Okay. All right. So that's all. I'll leave you with that, and you should work out this exercise as well as the exercises that we will put out. All right. We continue with the topic of logic. Today we will introduce a notion of quantifiers. So recall that we define predicates as as functions which assign a truth value, true or false, to every element in the domain. So you can have a predicate like winged, and Alice is not winged, Jabberwock and Flamingo are winged. So that's what the table shows you. So the predicate forms a column in this table, and you can apply this predicate to any element in the domain, and you get a proposition, a simple kind of proposition, for instance, winged Alice. And then you can build more complex propositions using operators and formulas. So that is the propositional calculus that we saw last time. What we'll see today is a way to build more complex propositions using a different technique. And the new thing that's involved here is called quantifiers. So we'll see what that is. But let me start with an example. So suppose I want to make the claim all characters in my domain, Alice in Wonderland, are winged. Okay? Or more elaborately, I'm claiming that for every character X in Alice in Wonderland, the proposition winged X holds. So X is a variable here, and I'm claiming that as you substitute the values Alice, Jabberwock, and Flamingo for X, in all cases, the predicate winged X will turn out to be true. Now, this proposition is a false proposition, but it's still a useful kind of proposition to state. And this is exactly what we can do now. And the notation for writing this proposition is, so you read this inverted A as for all. So for all X, winged X. This is the first kind of new statements that, new propositions that we are going to allow ourselves. By the way, I should have been more precise and said it's for all X in the domain Alice in Wonderland. This would be important when there are multiple domains that we are talking about. If we are making statements about integers and real numbers and rational numbers, I might want to clarify which domain I'm talking about. For us, in this section, we don't really have multiple domains, so I'll just omit that the description of the domain. So I'll just say for all X, winged X. Okay, the second kind of statement we can make are of the form, some character in Alice in Wonderland is winged. Okay. This happens to be a true statement because there are some characters. Or put another way, I'm saying there exists a character X such that winged X holds. Okay, so there is some value you can substitute for X from the domain such that winged X holds. And in notation, this looks like, so the inverted E you would read as there exists. So there exists X such that winged X. Okay. So this is what's called quantified propositions, and this new system where you're also allowed to talk about quantified propositions forms what's called predicate calculus. So it has these variables, and you can make statements about, you can use those variables to make statements about an entire column in this table. And as we'll see later, you can also use this to implicitly define new predicates from existing predicates. So this is called predicate calculus, or more precisely, first order predicate calculus. Higher order logics would let you refer to, so here we are letting ourselves refer to all the elements in the domain. If you also want to refer to more complex things like sets of subsets of the domain, or functions over the domain or other predicates over the domain, then that will become higher order logics. We won't go into that in this course. Okay, so it's just, when I say predicate calculus, I always mean just this. You are allowed to write these quantifiers for all x and their x is x to refer to all elements in the domain. So why are they called quantifiers? So basically these are statements about to what extent a predicate evaluates to true in the domain. Okay, so when I say for all x winged x, the claim is that it evaluates to the maximum extent. It evaluates to true, throughout the domain, right, to the maximum extent possible. And their x is just say, okay, there it's not zero, it's not never. There is some place where it does evaluate to true. So these are called the universal quantifiers, saying everywhere, and existential quantifiers, saying somewhere. Of course, you might then wonder, what about intermediate things? Could I say in half the domain? Or you can, and if you have appropriate notions of measuring the domain, there are other kind of quantifiers you could talk about, or even quantifiers like, the statement holds for an even number of elements in the domain, things like that. We again won't need any of that in this course. So for us, the only quantifiers of interest, and this is the case for predicate calculus, would be for all and their x's. Okay, so I said, we needed this new vocabulary so that we can make these statements. But there's another way we could have made the same statement. For all x winged x, we could have just gone ahead and written it as, winged Alice and winged Jabberwock and winged Flamingo, right? So we just go over every element in the domain and do a conjunction of the predicate applied to that element. So basically, I'm saying that instead of making a statement about the column, what you could do is make a statement about every cell in that column and then put it all together, right? So this is something you could have done. And similarly, for their x is x winged x, you could have written it as winged Alice or winged Jabberwock or winged Flamingo. And to some extent, actually, that's all that is to it. But the important difference is that, okay, first of all, it's much more compact. You don't need to write, you don't need to enumerate over your entire domain. But more importantly, this works only if your domain is finite. If I want to talk about all integers, a statement that holds for every integer, I cannot enumerate over all the integers because there are infinitely many of them. So that's what these quantifiers, that's the power that these quantifiers get you. You don't need to enumerate over the entire domain. Even if the domain is infinite, you will be able to make a statement using these quantifiers. Okay, so a couple of quick examples to get you familiarized with this. So here is a statement, here's a proposition. For all x, winged x, if and only if flies x. Okay. So one way to think about, whether the statement is true or false is to actually look at this part, winged x, if and only if flies x, as another predicate, as a new predicate. So for each value of x in the domain, this evaluates to something. So it assigns a true or false value to each element in the domain. So here is my new column, new predicate. I'm just calling it winged x if and only if flies x. You could use a different name so that this x doesn't appear twice in that heading. But this is what it is, right? And how did I fill in this table? Everywhere I took, in each row I took this winged Alice if and only if flies Alice. Well, that says false if and only if false. And if you remember the if and only if operator, this evaluates to true. Right? It's just saying, false equals false. So that is a true. The result of this applying the operator is true. And similarly, true is equal to true. So this entry is true, and the last entry is also true. So every entry in this column happens to be true. So for all x winged x, if and only if flies x is a true proposition. Here's another example. There exists x such that winged x implies not flies x. Okay, so there exists some x such that if x is winged, then x does not fly. Okay, so why don't we just write that out? So so there's my new predicate. Winged x implies not flies x. And you might think that, okay, we already have a statement saying winged x is exactly the same as flies x, and here it's saying something like winged x, if winged x then not flies x, right, for some x. So it might look like this is going to be a false statement, except you have to be careful with your intuition when there are vacuously true statements involved. So here, winged x implies not flies x is vacuously true for x equal to Alice, because winged Alice is false. Okay, so even though so then it doesn't matter what flies Alice is, right? Once winged Alice is false, the proposition winged Alice implies anything is true, vacuously true. So this entry here is true. The other two entries happen to be false because winged Jabberwock and winged Flamingo are true, and the negation of flies x is false, right? And true implies false is a false proposition. So these two happen to be false. But the claim I made is only there exists an x such that this holds. So this proposition is also true. Here's one last example. For all x, pink x implies flies x. So let's just look at those two columns, pink and flies. And let's also write down pink x implies flies x, the column. So again here, so flies x is false, sorry, pink x is false. So this is indeed vacuously true, that pink, so false implies false is vacuously true. False implies true is also vacuously true, and true implies true is true. So in all cases, this is true. So this proposition is also true. All right, so let me do one more example actually, and to show you negation of these kind of propositions. So let's take the proposition that we just saw for all x winged x, okay, which just happens to be false. So why is it false? Well, it's what is it saying? First of all, it's saying not everyone is winged, right? Or rather, for all x winged x is saying everyone is winged, and the fact that it is false is saying not everyone is winged. And that's same as saying there is someone who is not winged, right? It's not the case that everyone is winged. It's the same as saying there is someone who is not winged. So if I were to write this in notation, this looks like, there exists someone who is not winged. So there exists some x such that not winged x, okay? And this is a true statement, right? So if I were to build another column for not winged x, then you would see that, yeah, there is someone who is not winged, okay? So this is a true statement. And this statement here is actually the negation of this statement. So for all x winged x says everyone is winged, and the negation of that is not everyone is winged, which is that there is someone who is not winged. So more generally, I can write this kind of an equivalence for any, there's an equivalence I've written for any predicate W. Okay, so W here, you should think of it as any predicate. So this is just like we had equivalence of formulas, here, equivalences in predicate calculus, I would refer to predicates, and any predicate could be substituted there, and so any column, any kind of values on the column you can use for your predicate W, and still the statement would be true. As in, these two would be equivalent. So what are they? What is this saying? This is saying the negation of for all x wx is equivalent to their x is x, not wx. Now, this might kind of remind you a little bit of De Morgan's law, which had, and become or, and the negation move inside. And if it looks a little bit like that, that's because it is exactly that. So if you go back to what we said about how you think of for all x wx as just a conjunction of several statements like W Alice and W Jabberwock and W Flamingo, right? So in our domain, so those are the three elements. I've written it as AJF here. So for all x wx, simply it doesn't matter what predicate W is, it's the same as saying WA and WJ and WF. And its negation, you can use De Morgan's law to expand it out. We saw De Morgan's law applied to a conjunction of two elements. Here there are three elements, but this is just applying De Morgan's law twice, right? You could initially consider, say, WJ and WF as a single proposition. So this is WA and that single proposition. When you negate it, it becomes not WA or the negation of this proposition. And the negation of this proposition is not WJ or not WF, right? So what you get here is just by applying De Morgan's law twice to this. And if you look at what this is saying there x is some value AJ or F for which not WX is true. Right? That's what this distinction is saying. So, so it's just De Morgan's law that I'm writing here, except of course it's a little more general because it applies even to infinite domains. Okay. So this is what I want you to remember from the slide. Negating a statement for all x wx is the same as writing their x is x such that not wx. Okay, and this you should think over until it becomes comes completely naturally to you. And an analogous statement holds, of course, by looking at if I move the negation sign to the other side, then negation of their x is x. Let's call this as something else, say u. So negation of their x is x ux is the same as for all x negation of ux, right? So that's the analogous statement of negating a their x's statement. So when you negate a their x's proposition, you get a for all proposition, and vice versa. Do pay attention to that you need to negate the predicate inside. Okay, so let me now move on to predicates over more than one element in the domain. Okay, so far whatever we saw, the predicate was over a single element in the domain. So we thought of the domain as just as Alice, Jabberwock, Flamingo. But here is another way to think of the domain if you want to define a predicate over two elements. So here is a predicate likes xy, by which I want to signify that x likes y. Okay. And since there are two parties involved now, I need to write this for every pair xy. I need to write the value of likes xy for every pair xy. So I list down all 9 pairs of x comma y here. And for each of them, I can write down whether x likes y or not. Okay, so Alice likes herself. She also likes Flamingo. Jabberwock likes itself. and the flamingo likes itself, and nobody else likes anybody else other than this. Okay, so that's my new predicate likes, and I have defined it. It's defined in some sense over the same domain, but since it takes two inputs, it's a function that takes two inputs, really its domain is the square of the original domain, right? Okay, now let's take that example, and now let's, and now that there are two inputs to this predicate, I will be able to make some complicated and more complex propositions that involves quantifying over both these variables. So here is an example. I make a claim for all xy, for all pairs xy, likes xy, so x likes y. Okay. Well, is it true? This is claiming that every entry here should have been true, but it's not. So this is, everyone likes everyone is a false claim. Okay, false proposition. All right, here is another proposition. For all x, there exists some y such that x likes y. Okay. So how do we parse this? So we said for all x, I can write some function, some predicate of x, but this looks like a slightly different kind of expression. But okay, first of all, in English, what is this supposed to mean? This is supposed to mean for everyone, it is the case that there is someone that they like. Okay, so everyone likes someone. And that is true in our example because everyone likes themselves in particular. So this is the true statement. Okay. And let me give one more statement and then see it in English before I expand on this. So here is a statement: there exists y such that for all x, x likes y. So what is this saying? There is somebody such that for everyone, such that everyone likes this somebody, right? Every x likes this y. So there is someone, some y, who is liked by everyone. And that unfortunately is false. Jabberwock likes itself, nobody else likes Jabberwock. And Jabberwock likes nobody else. So there is nobody who is liked by everyone. Okay, so there's a false statement. Now, okay, so the point here is to first point out that the order of quantifiers is important. Okay, so these two statements look exactly the same. There is x and y and likes xy, except, and there's for all x in both cases, there x is y in both cases, but for all x comes first and their x is y comes next in the first statement, and here the order is reversed and they have completely different meanings. One proposition turns out to be true, the other turns out to be false. So the order is important. Okay, so let's see this once more. So going back to the original notation we had, I said for all x, it has to be some predicate of x, right? So this, on the face of it, doesn't look like a predicate of x, but I can just make a predicate. Okay, so I just rearranged my table a little bit. So I just collected things by x and then wrote y, for each x I wrote all possible y's. And there's the same original likes xy function predicate. And what I'm going to do now is, though, this part, there x is y likes xy, I'm going to think of that as some property of x.